we're going to be talking about some surfaces in space. We've actually already talked about two different surfaces, and that would be, there we go, spheres and planes are examples of surfaces. I have on the screen the equation of a sphere and the equation of a plane. Hopefully those look familiar as we talked about them in previous sections. So when you have an x squared, a y squared plus a z squared, that's going to give you a sphere. A plane has linear terms, so an x plus some y plus z linear terms gives you a plane. So what other types of surfaces might we have, and how can we identify what they look like? By just looking at their equations. That's our goal in this section. So let's start by just doing an example. We are going to sketch the graph of y squared plus z squared equals 9. Now this is what's considered a cylindrical surface, and I'll explain what that means, but let's just go about graphing this. So the very first thing I'm going to do is I notice that this equation, it actually doesn't have any x's in it. It only has a y and a z in it. And so what that means is if I look at this in the YZ plane, so if I just look at this in the YZ plane, I should see a circle centered at the origin with a radius of 3. So it's going to be in the YZ plane because it has y's and z's. And so I've tried to sketch that on my graph paper, my three-dimensional coordinate system, that in the YZ plane, it's just going to look like y squared plus z squared equals 9, which is a circle of radius 3. Now, because this equation doesn't have any x's in it, what that means is as I move along the x-axis here, wherever I am on the x-axis, if I take a slice through that graph, I'm always going to see the exact same thing, a circle with a radius of 3. And so let me try to draw that on my graph paper. So at any x value, wherever you are slicing this along the x-axis, you're going to see that exact same circle. And so that's what I've tried to draw on my graph. And so this is the graph of a cylinder. That's why it's called a cylindrical surface. This is actually a cylinder for this one. A little bit of vocabulary word. When I drew my graph, to help us kind of see what we're looking at, I put these kind of lines that I guess paralleled the x-axis, and those are known as rulings. Rulings are I guess parallel to the axis that it runs along, kind of gives you a view of what you're looking at. So that's a common way to sketch the graph of one of these cylindrical surfaces. All right, let's do another one. Let's take a look at another cylindrical surface, see if we can make some comparisons. Before we do that, here's a definition. The equation of a cylinder whose rulings are parallel to one of the coordinate axes contains only the variables corresponding to the other two axes. Okay, so what this statement I have on the screen is telling us, if we go back to the original example that I did, notice that this equation doesn't have an x in it. It only has a y and a z. And so its rulings are going to be parallel to the missing letter. So there's no x. So the rulings are going to be parallel to the x-axis. And that's always going to be true if you have an equation with only x and z and it's missing a y, it's going to have rulings that are parallel to the y-axis. And what does that mean? That means if you slice it along, in this case the x-axis, it's always going to look the exact same. All right, so here's another example. Let's try to sketch the surface z equals sine of y. So this equation does not have an x in it. So the rulings are going to be parallel to the x-axis. That means if I slice it, if I make cuts along that x-axis, I will always see the exact same image, the exact same graph. Okay, so I am going to start by just sketching the graph of z equals sine of y, just in the yz plane. And so I put some tick marks on my graph paper. Since it's sine of y, the y-axis represents the angles. So I put pi and 2 pi as my tick marks. And then the z-axis is the outputs. So a sine wave is only going to go up to 1, down to -1. And so I'm just going to sketch a sine wave in that yz plane. So I just remember this from trigonometry. The sine wave goes through the origin. It makes one complete period in 2 pi units, or one trip around the unit circle. So that's what I have drawn. It goes up until you get to an angle of pi, and then it goes down until you get to 2 pi. So that's my graph of a sine wave. I've just drawn it in the yz plane. And then this is technically what we call a cylindrical surface because it's missing the x variable. That means what we're going to see is this exact same shape all the way along the x-axis. And so I'm going to draw some rulings, or just parallel lines that run parallel to that x-axis. So my drawing's not great, but it kind of looks like, to me, this particular shape. It's almost like you took a piece of paper and you kind of put some folds in it in the shape of a sine wave. That's exactly what this surface is looking like. All right, the next type of surfaces I want to run through in this video are what we call quadric surfaces. And those are basically three-dimensional versions of our conic sections. So on this slide, I have just a review of conic sections. You might have seen this in a college algebra course, or maybe in Calc 1, maybe in Calc 2. Maybe you haven't seen conic sections. Hopefully you've seen some of these. But here on the screen is a very quick overview of the different types of conic sections and what their equations look like. And so notice that when you have, if we look at this first one right here, circles and ellipses, we have an x squared plus y squared. That's going to give us either a circle or ellipse. If the a and b are the same, we have a circle. If they're different numbers, we have an ellipse. But the important thing there is the x squared plus y squared gives us a circle or an ellipse. If we have only one variable squared, then we have a parabola. If it's the x squared, the parabola either opens up or down. If it's a y squared, the parabola is going to open sideways. Positive y squared opens to the right, negative to the left. So that's our parabolas. And then finally, we've got hyperbolas, and that occurs when you have an x squared minus y squared, or vice versa. So I bring this up because I think it's helpful to make some comparisons to our three-dimensional conic sections with two-dimensional conic sections. Putting that information together, I think, is going to be helpful. All right, so let's go to the new stuff, the quadric surfaces. And so I'm just going to run through the different types of quadric surfaces or conic sections in 3D that we might have. And so the first one is called an ellipsoid. This is our three-dimensional ellipse. And if you think back to 2 dimensions, our equation of an ellipse was an x squared plus y squared. And so this is really similar. It's an x squared plus y squared plus z squared is going to give us what we call an ellipsoid. If a, b, and c are all the same number, then we have a sphere. But basically, when you have an ellipsoid, what that means is if I slice it in the direction of the z-plane, I'm going to get an ellipse. If I slice it along the y-axis, I'm going to get an ellipse. And if I slice it somewhere along the x-axis, I'm going to get an ellipse. So I've tried to draw what I mean by that. So if I make a slice along the z-axis somewhere, that cross-section is going to be an ellipse. The same is true if I take a slice along the y-axis or the x-axis. And so that's what we call an ellipsoid. And just like in 2 dimensions, those numbers A, B, and C give you information about distance from the origin in each of those directions. All right, we can have hyperbolas in 3 dimensions as well. They're called hyperboloids. This is an example of what we call one-sheet hyperboloid, because you can make it with one sheet of paper. The thing to notice about the equation here is our hyperboloid has 1 plus sign, 1 minus sign. They're all squareds, equals 1. So that's the thing to notice. So we've got 2 squared variables that are being added, and then 1 is being subtracted, equals 1. The axis of the surface corresponds with the variable with the negative coefficient. So what I mean by that is you notice that the z variable is the one that's negative, and so the axis of the surface would be the z-axis here. You could call it an axis of rotation. You could think of it as kind of the middle of the surface. When you have a one-sheet hyperboloid, what's happening is along the z-axis, if you make a slice, you actually get something that looks like an ellipse. So if I chop it along the z-axis, it's going to look like an ellipse, but in the y or the x-axis, it's going to look like a hyperbola. If we have 2 negative signs, it's going to be a 2-sheet hyperbola. So 1 negative sign is a 1-sheet hyperbola. 2 negative signs is a 2-sheet hyperbola. It just means we have this kind of gap right here. So there's a place where there is no surface. Or you could think of it as you would need 2 pieces of paper to build this surface. So this is really similar to the 1-sheet hyperbola. With really the only difference is that in plane Z, so if you cut it in the Z direction, if you're in the middle here, again, you're going to get nothing. But once you get high enough or low enough, then you will get ellipses in the Z plane. But it's hyperbolas if you slice it in the Y or the X direction. All right, our next surface is the elliptic cone. And the elliptic cone, the really big difference here, notice it equals 0. If we go back, the hyperbolas, or hyperboloids, I should say, as well as our ellipsoid, they all equaled 1. They had a constant term in them, basically. But our elliptic cone has one side equal to 0. It doesn't have a constant term in it. And what that means is if you're actually in the XZ or YZ plane in this case, you're going to see lines. So some of the cross sections are actually linear, are lines. And then once again, this is similar to our one-sheet hyperboloid. The axis of the surface corresponds to the variable with the negative coefficient. So the Z is negative. And so I would say the axis of the surface is Z. You could think of that as an axis of rotation. The surface is wrapping around that axis. All right, we also have what's called an elliptic paraboloid. So here is what an elliptic paraboloid looks like. The thing to notice about the equation of our elliptic paraboloid is we have one linear term. So the z right there is a z to the 1. It doesn't have a squared in it. And then the other 2 variables are squared. and they're being added together. So that's what I notice about this equation. This is what we call an elliptic paraboloid. Oh, let me go back. Because in the z-plane, we get an ellipse. So it looks like, it's not a good color, that's hard to see. Kind of looks like an ellipse in this direction. But in both the x and the y plane, if you cut it along the x or the y axes, you're actually going to get a parabola. You could also think of it as, it kind of looks like to me like if you took a parabola and you kind of spun it around like that. And then we also have what's called the hyperbolic paraboloid, and that has a linear term. So one of the variables is linear, in this case the z. It has two squared terms, but the difference between this and the elliptic paraboloid is there is a minus sign right there. And so basically what that does is you still have a paraboloid, or a parabola, lots of words here, in plane y and in plane x, but those parabolas, let me go to the parabolas, there we go, open in opposite directions. And so it gives it this kind of saddle look to it. And in fact, it's appropriate to describe this shape as having a saddle to it. So you have in one direction kind of a parabola that opens up, but in another plane you have a parabola that opens down. And then if you slice it around along the z-axis, you actually do get a hyperbola. All right, so that's kind of a quick summary of our quadric surfaces. And so let's see if we can classify the surface. Then we're going to find the xy trace, the yz trace, the xz trace, and sketch the graph. So I'm going to have to define some words for you as we do this problem. Okay, so first step, classify the surface. And so I'm going to look through that list of quadric surfaces and see which one is this. And immediately the thing I notice is I have a linear term, and then I have the sum of two squares. So this is kind of like my parabola in 3 dimensions. It would be a paraboloid, and because the squared terms are being added, it's our elliptic paraboloid. Okay, so that's step 1. We classified the surface. This is elliptical paraboloid. All right, the next thing we're going to do is find the xy trace. And so what does that mean? What is the xy trace? So the xy trace is basically asking what does the graph look like in the xy plane? So if we were to take a slice of this object when z equals 0 in that xy plane, what is the shape that we would see? And so to answer this question, we're just going to plug in z equals 0 into the equation. And that's going to give us what this graph is going to look like in the xy plane. So when z equals 0, we're just left with x equal y squared. So we're just left with a parabola. So in the xy plane, it looks like a parabola with a y squared. And then we can do the same thing for the other traces. So if I want to find, here we go, the yz trace, I would plug in 0 for x. And so if we plug in 0 for x, we're left with 0 equals y squared plus 4z squared. Let's see, if you square a number, you always get a positive, or 0, I guess. And so the only way this statement can be true, the only way you're going to get a true statement when you have a squared plus a squared, is if both of those numbers, both y and z, are 0. So if y or z is anything other than 0, you're not going to get a solution to this equation. And that's just because there's no way you can get a 0 if you add two positive numbers together. So the YZ trace here is technically only one point. It's the point 0, 0. So this equation is only valid at the point 0, 0. Okay, and then our XZ trace, what happens when y equals 0? So I just plugged in 0 for y, and I have the equation x equals 4z squared. That's another parabola. Okay, so I classified the surfaces, I found the traces, and now I'm going to sketch the graph of this thing. And so a great way to sketch the graph of a surface is to start by drawing those traces. And so I'm going to start by drawing what's called my XY trace. And so I'm going to think about on that YZ plane, grab my highlighter, here it is. I'm going to be drawing the equation x equals y squared on the YZ plane. And so this is a parabola with a vertex at the origin. It's a y squared, positive. So if we were just graphing this in 2 dimensions, it would open to the right. And so in my picture right here, in this YZ plane, my parabola opens to the positive x-axis. So that's my XY trace. And then my YZ trace is just a point. There's really nothing to graph there. But in the XZ plane, so I know it's hard to see when you're just looking at a picture, but so if I think about what does it look like in this XZ plane here, I'm also going to see a parabola. And that parabola is also going to open to the positive x direction. And so I've tried to draw that in orange, that there's another kind of parabola in this XZ plane as well. And then this is an elliptical paraboloid, so that means now that we know the direction of those parabolas, they're connected by these ellipses along that x-axis. So there we go, tried to draw that. It's a little sloppy, but gives us the kind of basic idea of what's happening here. So if we were to slice this along the x-axis, we're going to see a bunch of ellipses. We see parabolas in the XZ and YZ plane. So there's my elliptical paraboloid. All right, let's do another one that's similar. So same instructions, different equation. Classify the surface. Find its XY trace, its YZ trace, and its XZ trace, and sketch its graph. So for this particular equation, the x, the y, and the z are all squared. So all of the variables are squared. There's no constant term. And so if I were to, for example, put all the variables on one side, it equals 0. And so that would be my cone. The cone is the example where there is no constant term. All right, so XY trace, what happens when z is 0? So I plug in 0 for z, and I'm left with y squared minus x squared equals 0, or x squared equals y squared, or x equals plus or minus y. So my XY trace is actually a set of lines. Y equals x is a line, y equals negative x. So my XY trace would be 2 lines. My YZ trace, if I plug in 0 for x, I get 0 equals y squared plus 2z squared. And once again, that is just a point. That's the point 0, 0. The sum of 2 squares is only equal to 0 when they're both 0. And then my XZ trace, what happens when I plug in 0 for y? If I plug in 0 for y, I end up with x squared equals 2z squared. Take the square root. I get x equal plus or minus root 2z. So in the xz plane, this object also looks like two lines, two intersecting lines. So let's put this all together. I'm going to start by trying to graph my xy trace. So I'm thinking about what does this graph look like in the xy plane. So if I were to just take a slice of it in the xy plane, I would just see two lines. I would see the line y equals x, and then I'd also see the line y equals negative x. So that's what I've tried to draw here. Here's my line y equals x, and it goes back behind here as well, and then y equals negative x is that line right there. The YZ trace, there's not really anything to graph there, it's just my point, but my XZ trace is also two lines. So again, I'm thinking about in this XZ plane right here, below as well. What does the graph look like in that XZ plane? Well, it also looks like two lines that go through the origin, one of them with a positive slope, one with a negative slope. So this would be like x equal plus root 2z, and then down here x equal minus root 2z. In terms of the graph, it is perfectly fine if you're not completely accurate on graphing points. Really the purpose of these drawings is to identify the structure of these shapes. That's really going to help us out later on when we're solving problems about regions in space. If we can visualize what's happening, it's really going to help us solve those problems. And so, do you actually need to find out where is square root of 2? Where is that point on here, and plot points? No, I don't expect you to do that level of accuracy. I really am just looking for the appropriate shapes here. And so you definitely don't have to plot points. Your graph doesn't have to be perfect. I'm looking for the fact that, okay, we've got lines in the XZ plane. We also have lines in the XY plane. And then if we put all of this together, we're going to end up getting a cone. And so you're going to see basically circles or ellipses if you slice it along the x-axis. And so that's what the graph of this particular cone looks like. All right, I think it's really important to be able to look at these equations, pick out which of our quadric surfaces we have, and identify them. But drawing a picture is really hard. It takes a lot of practice, and as you can tell, I've had some practice and I'm still not very good at it. And sometimes, especially when you have a more complicated surface, it might be nice to just make a computer generate the graph for you, and that will really help you look at that particular surface. With that said, I still think you should be able to come up with a picture and a very rough sketch by hand. I do think that is an important skill to have in this class. But in terms of an accurate sketch, that's really hard to do by hand. So we can use technology to graph these things as well. And this is a website I really like for creating graphs of both surfaces. It can do lines in space and other types of curves in space. And so this CalcPlot 3D is the website I like to use. And I'm happy to spend some time in class talking a little bit more about it. But for now, I just want to kind of show you a quick overview of how the site works, and you can play with it on your own. So right now, just when you go to the website, it by default graphs something for you. So it has graphed this equation right here. And so I'm just going to click on this X right next to that equation just to remove the default. So I just deleted that. And then you've got this drop-down menu that is going to allow you to type different curves vector fields, which we'll talk about later. You can plot vectors, all different types of things with this drop-down menu. And so if I want to graph, say, the cone that we just graphed by hand, since that equation was not solved for z, so if they're solved for z, I just pick function. But if it's not solved for z, I go down and I pick implicit surface. And then it filled something in for me, so I'm going to delete that. And I'm just going to type in the cone we were working with, which was x squared equals y squared plus 2z squared. And then you can play around with the range of x, y's, and z's. I'm going to leave it as it is for now. But to make it appear, you just have to check that box to the left of your equation. And there's my cone. And the thing I really like about this website is you can just take your cursor or your mouse and you can kind of drag this around. And so you can really see a nice picture of what's happening. What does this particular surface look like? So this is a great tool that will let you check your work when you're graphing something by hand. Or if you have something that's more complicated than just a quadric surface, we can use this tool as well. And so while I have it up on the screen, maybe I'll graph my paraboloid as well and make sure I did that correctly. So we had in the previous example, x equal y squared plus 4z squared. I think I have to click enter. There it is. There's that paraboloid that I had graphed earlier. Looks better than my picture. All right, that was my last example for this section. As always, please let me know if anything was unclear, and I'm happy to try to explain something in a different way or clear things up.